Hi, I'm Herb Gross, and welcome to Gateways to Mathematics. It's sort of a bittersweet occasion from my point of view. This is the last enrichment lecture, and I hate the speaker who starts off by saying, before I begin speaking, there's something I'd like to say. But there really is something I'd like to say. I haven't met you personally, but it's been a labor of love to be able to deliver these lectures to you, and I just hope that your own personal horizons have been expanded by this. And if the program has brought you half the satisfaction that it's brought me, it's been a tremendous experience. So with that in mind, we now turn to more mundane things like formulas. And formulas are kind of strange things. They range from the sublime to the ridiculous. I'm always reminded of the story of the man who found the fast way of counting sheep. He used to count the legs and divide by 4. See, that kind of a formula. I used to have trouble in a room. You know, when you want to count the people in the room, I always used to forget whether I counted myself or not. So in my whole life, I've only invented one formula. All the rest I've stolen from other people. The gross formula is when you want to count the number of people in the room and you want to make sure you count yourself, you start with yourself, you end with yourself, and you subtract 1. That's my formula. But the other problem with formulas is that sometimes they work and sometimes they don't. I'm reminded of a story of the geography professor who said to his class, "Class, I have a very difficult question for you. If we're bordered on the north by Canada, on the south by Mexico, on the east by the Atlantic Ocean, and on the west by the Pacific Ocean, how old am I?" And not one person in the class knew, except one kid. He raised his hand. He says, "You're 42, Professor." And the professor says, "That's amazing. But how did you ever figure that out?" He said, "Sir, it was simple. I have a brother in a mental institution who's 21, and you're twice as bad off as he is." Well, that's a terrific little example of a formula that works once and only once. You see, the next year, that formula isn't going to work, because 1 year later, the brother is going to age by 1 year, but we're going to be multiplying by 2 when you double. So what are the problems with formulas? The first problem is, how do you get the formula? The second problem is, how do you know the formula works? I'm going to talk a little bit about that to you, but the bottom line is going to be, if you don't panic and you understand what we've done in the course so far, all you're going to have to do is see the formula and you'll get the answer without even knowing where the formula came from. So without further ado, let's go back to the board and take a look and see how far we've come so far in our course in terms of being able to handle formulas or not being able to handle formulas. Do you remember our humble origins? The very first program, we said things like, how much is a quarter, dime, and nickel versus how much is 1/4 plus 1/10 plus 1/20th. And we pointed out at that particular time, this problem didn't give us trouble because we were familiar with it, but this we didn't recognize as a disguised version of the same problem. Hopefully, by this point in the course, not only does this not bother you, but you just, in a very quick way, dash off the answer here. In other words, with 4, 10, and 20, 20 is the least common denominator, 1/4 is 5/20ths, 1/10 is 2/20ths, 1/20th is 1/20th. You add these up, you get 8/20ths, which reduces to 2/5, and in terms of money, 2/5 of a dollar is 40 cents, and there's the same 40 cents that we get the other way. But now you see the problem becomes compounded, because what happened was we gave a pair of problems, one of which was easy, one of which was hard. As you gain knowledge, the hard one becomes easy because you now know more. But there's always a companion that goes with it. You see, before we knew the quarter, dime, and nickel, but we had a hard time with the fractions. Now the fraction problems don't bother us, but maybe applying them does. See, for example, I say, how much is 1/3 plus 1/6? Well, you say, let's see, the common denominator is 6, 1/3 is 2/6, 1/6 is 1/6, the answer is 3/6, 3/6 reduces to 1/2. Okay, so now I give you this problem, and we've talked about similar things before. I say, John can paint the fence in 3 hours, Bill can paint the same fence in 6 hours. How long will it take if they work together? Now you see, this problem doesn't seem related to the one that we just did. But assuming the usual conditions of they work at the same rate and they don't get in each other's way, if John takes 3 hours to paint the fence, he paints 1/3 of it per hour. Bill does 1/6 of it in an hour because it takes him 6 hours. So working together, they do 1/3 plus 1/6 of the fence. That's 1/2 the fence. You see, that's the problem we just did. But in this problem, you have to know that you want to add the 1/3 and the 1/2. See, so if they do half the fence in 1 hour, they'll do the whole fence in 2 hours. So now what formulas do is they go one step beyond that. See, what the formula does is you say, okay, take the number of hours it would take John alone. And the reciprocal of that would be how much he does in 1 hour. Take the number of hours it would take Bill working by himself. The reciprocal of that would be how much Bill does in 1 hour. Add them together. That will be how much of the total job, which we'll call N. N will be the whole job. That will be the fractional part of the whole job they do if they work together. So the formula now becomes 1 over N equals 1 over J plus 1 over B. Now, even if I don't know how I got this, if I now say to the person, find the value of N when J is 3 and B is 6, all that person has to do is go to this formula, replace J by 3, B by 6, and solve this equation. And how do you solve this equation? Well, we already know that 1/3 plus 1/6 is 1/2. So if the reciprocal of N is 1/2, N will be the reciprocal of 1/2, which would be 2. See, if 1 over N is 1 over 2, if I flip them, N over 1 will be 2 over 1. Now I get that the answer is 2 hours without even having to know why the formula works. You see, as long as you trust the person who made up that formula, that's the same as knowing the formula. So all you really have to know is what? Not to be uptight. Trust the formula, do what you're told, and trust your elementary mathematics. But the advantage of understanding the formula is you also know its limitations. For example, in this problem, you assumed that Bill and John can work together and work without getting in each other's way and do proportional parts. You see, suppose the problem now says John can climb a mountain in 3 hours, Bill climbs the same mountain in 6 hours. We talked about this in a different context before. How long does it take if they climb it together? You see, the formula 1 over N equals 1 over J plus 1 over B. That formula is still a true statement, but not for this situation. You see, the problem over here is they don't work independently. If they're climbing this together, the faster guy has to slow down to the rate of the slower guy. In other words, they can't climb the mountain any faster than the slower fellow can do it in this case. So this formula, although it works in one particular situation, doesn't work in another situation. So another important thing, why it's so important to understand your subject matter as well as the mathematics, is not only should you be able to use a formula, but you should understand when that formula is applicable and when it doesn't. We have had problems in high technology where people have used a wrong formula and the airplane takes off and the wing falls off. And when they asked the fellow, why did it fall off? He says, I don't know, I used this formula, and it turned out that that formula didn't apply for that particular situation. These are true stories of tragedies that happened, not because people didn't know how to use a formula, but they used a formula that wasn't supposed to be used. So even if I give you the formula, I'm trying to warn you, make sure that the formula fits the given situation. Always check under what conditions a formula is supposed to work. And we'll talk about that more as we go along. Now, if you recall in our previous lecture, I showed you how one converts from Fahrenheit to Celsius. And I thought that what I'd like to show you is that that formula wasn't just pulled out of the hat. I'd like to show you how that formula came about, but also to emphasize that just as you were doing problems last time before we saw how the formula came about, you can do the same thing now. I just think it's much more enlightening to see how the formula comes about. Basically, the whole principle behind a thermometer is that in general, heat expands and cold contracts. You can always remember that by the little joke. The teacher said, give me an example of how heat expands and cold contracts. And the little kid said, in summer, the days are long, but in winter, the days are short. It's a great story, but it doesn't work for the nights. But basically, when you heat something, it will expand, and when you cool something, it will contract. So the principle behind the thermometer is you make a very narrow opening in a tube, you fill it with a liquid, then you see when you heat that liquid, the liquid expands. Because the opening is so narrow, it doesn't have room to swell out, so it moves up the tube. You see, it's got no place to go but up. Isn't that a nice cliche? No place to go but up. And basically, that's the way the thermometer works. You have a reservoir in the bottom so that when the thing expands, it can draw the liquid from it. And also, when it contracts, it can draw back in here. Okay? And also, I've drawn this very wide. If you've ever broken a thermometer, you'll notice that the opening is very, very narrow, and what they have is a very big magnifying glass here. You see, if the opening was very wide, you wouldn't be able to notice the level rising. It doesn't happen that much. For example, take a pot of water, put it on the stove, heat the water, and before the thing boils, you won't see any noticeable increase in height in the level of the pan. You'd have to have what? A very, very narrow opening to see this. But that fact notwithstanding, this is the way the thermometer idea came about. And the first person to use this was a Dane named Fahrenheit. That's where the word Fahrenheit scale comes from. Now, what Fahrenheit did is he wanted to be able to measure temperatures. So he wanted a couple of markings that he could use as standards. So what he did was, it gets cold in Copenhagen. So what he did was, one cold morning, he stuck the thermometer out the window. And what the reading was that cold morning, he called 0 degrees. See, he called that 0. So 0 stood for a cold day in Copenhagen. What do you think, Ani? Does that sound like a nice title for a musical? A cold day in Copenhagen. Well, that's what happened. There was a cold... See, why did he pick a cold day? He picked a cold day because if he picked a warm day and called that 0, on a normal day, temperatures would be below 0. You see, he didn't like to work with below 0 numbers or negative numbers, so he picked 0 to be on a day that he felt was about as cold as it gets in Copenhagen. And you see, when 0 degrees Fahrenheit happens, it is a pretty cold day. Then he wanted to get a 100-degree reading. That's something a lot of people don't realize. Fahrenheit worked on a scale of 100 also. He got his 0 point by the cold day. Now he had to get his 100 point. And the way he did it was he took his body temperature, and he called that 100, which also has an interesting bit of folklore to it. Basically, either Fahrenheit read the thermometer inaccurately, or he had a slight temperature that day. In fact, probably anybody who cares about the cold morning in Copenhagen always has a slight temperature. But the point I'm driving at is that if Fahrenheit had had normal temperature that day, the normal human body temperature would have been 100 degrees Fahrenheit. In other words, the 98.6 seems to indicate that Fahrenheit's 100 was a little bit above normal. Maybe 100 was his normal temperature. But basically, you see, he built a scale of 0 to 100, where 0 was the cold day in Copenhagen and 100 was his body temperature. Which, by the way, are pretty subjective type of things. I mean, who really cares about one particular cold morning in Copenhagen and what Fahrenheit's body temperature was? Well, maybe some people care. I didn't mean it that way. It wasn't meant to be cruel. But the idea is this. We usually, in the world of science, like something a little bit more standard than that. So Celsius came along, and he said, he just made up a phrase. He said, who cares what a cold day in Copenhagen was like or what Fahrenheit's body temperature was one particular day? Let's pick something that's more standard. So what he did was he put the thermometer into a mixture of water and ice. And he kept adding ice until he reached the freezing point of water. By the way, there's an interesting scientific way of knowing when you've reached the freezing point of water. If you put the thermometer in water and keep cooling the water, the temperature of the water will go down. As soon as the water starts to turn into ice, all of that energy of cooling goes into making the ice. So the water stops cooling. In other words, you can tell when the ice is starting to form because the temperature stops dropping until the ice is already formed. So it's very scientific to figure out where this freezing point of water is. That's what he called 0. Then he boiled the water. And how do you know when you come to the boiling point? It's not just that it bubbles, it's that while the water is bubbling and turning into steam, the temperature doesn't change. See, it's called the latent heat of freezing and the latent heat of vaporization. It gets hidden, the temperature doesn't change. But the important thing was that Celsius called 0 the freezing point of water and 100 the boiling point of water. And you see, the freezing point and the boiling point of water are temperatures that can be produced in any laboratory. They become a standard that way. By the way, before the word Celsius, the word that was used was centigrade. Centi means 100, grade means degrees. So all centigrade means it was based on 100 degrees. But you see, Fahrenheit's temperature was also based on 100 degrees. I'm just telling you this folklore to have you see that science too, just like Shakespeare, can be told like a pseudo-love story. Things happened. They were exciting things. They changed the course of history. But let's just recount this as we go along. You see, a lot of my students just said to me, what made Fahrenheit say that the freezing point of water was 32 degrees? Fahrenheit never said that. You see, the freezing point of water occurred at a certain point on the scale that Celsius called 0. That scale didn't know whether you were looking at the Celsius side or the Fahrenheit side. You see, Fahrenheit already had his 0 and 100, and on his scale, the freezing point of water turned out to be 32 degrees. He didn't say let the freezing point of water be 32 degrees. He measured it to be 32 degrees on his scale. Then the boiling point of water, which was 100 on the Celsius scale, when you looked across on the Fahrenheit scale based on this particular scale, that came out to be 212 degrees. So that was how this thing started to happen. So you see, in other words, from the freezing point to the boiling point of water, on the Celsius scale it goes from 0 to 100. On the Fahrenheit scale it goes from 32 to 212. You see, but Fahrenheit 0 to 100 just didn't interest the science community. Now let me show you where the formula for converting Fahrenheit into Celsius comes from. Let's suppose that the mercury level in the tube is up to here. Okay? So on the Celsius scale, you're measuring from here to here. The height of this column is the same whether you're measuring in Fahrenheit or Celsius. Just the adjective is going to be different. So look at the height of this column. How big is this in Fahrenheit degrees? You're going all the way up to F, but you see the 0 comes opposite the 32. To get the true height, you have to subtract the 32 from this. In other words, if this was 68, the height of the column from here to here isn't 68 Fahrenheit degrees, it's 36 Fahrenheit degrees. So in other words, you subtract 32 from the Fahrenheit scale to bring it down to the 0 over here. Now, here's where that magic 5/9 comes from. Notice that the freezing point to the boiling point of water is 100 degrees on the Celsius scale. But what is it on the Fahrenheit scale? You're going from 32 to 212. 212 minus 32 is 180, so there are 180 degrees Fahrenheit per 100 degrees Celsius. Dividing both sides by 20, you see that there are 9 Fahrenheit degrees per 5 Celsius degrees. So Fahrenheit per Celsius is 9 over 5, or 9/5. But Celsius per Fahrenheit would be 5 over 9, or 5/9. See, in other words, the way this formula comes about is you say, look, we'll first subtract 32 degrees to find the height of this column in Fahrenheit. Now, since every 9 Fahrenheit degrees are 5 Celsius degrees, we only take 5/9 of this. And that's where the formula C equals 5/9 of F minus 32 came from. Now, some of you may be very excited by this and say, isn't that wonderful? Others might say, who cares? The important point is that whether you care or you don't care, if you ever have to convert from Celsius to Fahrenheit, if you know this formula, you just go and apply it, whether you use the algebra form or the verbal form. See, in verbal form, how do you convert from Fahrenheit to Celsius? You start with the Fahrenheit, you subtract 32, you multiply by 5/9, and the answer is the Celsius reading. Once you know this, how would you convert from Celsius to Fahrenheit? You would just reverse these steps. See, that's where the algebra comes in. You would just reverse these steps, interchanging multiplication with division and addition with subtraction. See, you would start with C, divide by 5/9, which is the same as multiplying by 9/5, and then add 32. See, I've summarized it down here. Starting with Celsius, you multiply by 9/5, which is the same as dividing by 5/9, add 32, and the answer is F. And if you now write that as an algebraic formula, you start with C, multiply that by 9/5, then add 32 onto the answer. You see, these two formulas look different, but they're simply two different ways of expressing the same relationship. This is the formula you'd use if you were given Celsius and wanted to convert to Fahrenheit. This is the formula that you'd use if you were given Fahrenheit and wanted to convert to Celsius. But in either event, what's the bottom line? Once you accept the formula, you can use it. Let me show you another famous formula, one that we use in the textbook just to give you some drill. It's the famous free fall body done by Galileo in a vacuum. In other words, how fast does a freely falling body fall near the surface of the Earth if there is no air resistance? And the amazing thing that Galileo discovered is that in a vacuum near the surface of the Earth, if you dropped a feather and a lead pellet from the same height, they would both hit the ground at the same time. Of course, we don't live in a vacuum, and people made fun of Galileo for even conjecturing that. But notice that in making tubes, tubes are sort of obsolete for many things, but the so-called vacuum tube was almost a perfect vacuum. In other words, even though we don't live in a vacuum, we can create vacuum conditions. But here's what Galileo observed. Galileo observed that in a vacuum, as an object fell towards the Earth from a stop position, well, in any position, its speed increased by 32 feet per second every second. We call that the acceleration, and we say it's 32 feet per second per second. That's what the square means over here, 32 feet per second per second. So when this problem started, the object wasn't moving. After 1 second, its speed was 32 feet per second. After 2 seconds, its speed was twice 32, or 64. In other words, how do you find the speed? You take the number of seconds and multiply by 32. So after t seconds, the speed is 32 times t feet per second. Now, how do you find the distance? This goes back to module 10 and 11. To find the distance, you use the average speed. When you say distance equals speed times time, you're talking about the average speed. How do you find the average speed if the rate of increase is constant? What you do is you take the speed when you started. Well, when there was no time, there was no speed. Take the speed at the end of t seconds, which is 32t. Add the two together, that's 0 plus 32t is 32t. Divide by 2, that gives you 16t. So in other words, if this thing has been falling for 5 seconds, the average speed during that 5 seconds will be 80 feet per second. So you take the average speed and you multiply that by the time. And if you write that in mathematical symbols, you get 16 times t, which we write as 16t squared, and we put the t squared in parentheses to indicate that only the t is being multiplied by itself. Then we adopt the convention that if the parentheses don't appear, it's understood that the exponent refers only to the factor immediately to its left. But basically, I've shown you very quickly how to derive this, and you say, my God, this isn't a physics course. I don't know what he's talking about. If you can follow me, that's fine. If you can't follow me, it serves my purposes just as well. Because what I'm trying to show you is the physicist shows how to get this formula. The person who wants to see how long it's going to take for the object to fall only has to use it. And by the way, this whole thing was based on the fact that you're in a vacuum and that you're near the surface of the Earth. If you try this in space, or if you try it on a windy day, the result isn't going to hold, because that wasn't the conditions under which the formula was obtained. And we'll talk about that more in a little while also. But the bottom line was that in a free fall vacuum near the surface of the Earth, an object falls d feet in t seconds. See the algebra language coming in to indicate that we don't know how many seconds we're talking about or how many feet. We say d feet in t seconds according to the rule d equals 16t squared. And what that means is that not only does the object fall faster and faster, but under the heading of the quantitative study of relationships, you see, this says, look, you start with the time, you square it, you multiply by 16, and that tells you how far the object fell. You see, it's not enough to observe poetically, my golly, this falls faster and faster. You have to be able in mathematics and in science to tell exactly how it happens. Now, if this formula here bothers you, this is why I want you to be bilingual between the algebra and the verbal. Go back and forth, just like when you learn a foreign language. If you're learning French, isn't there one section that says translate from English into French? Then another section that says translate from French into English? This is the same thing. I want you to learn to translate from verbal into algebraic and from algebraic into verbal. And that way you can shift to whichever one you want, depending on which one makes you feel better. But the verbal formula for free fall is this. Take the time that the object is falling in seconds, square the time, multiply that by 16, and the answer is the fallen distance in feet. And when you write that compactly in the language of algebra, it says d equals 16t squared. See, this and this say the same thing. What's the advantages and disadvantages? This shows you in a nutshell what's happening, but if you can't read this language, it's useless. This shows you word for word in a way that you can understand what's happening, but it takes a long time to write. At any rate, let's try to do a few problems this way. How far does such an object fall in 3 seconds? What does the formula say? You take the time in seconds, multiply it by itself, multiply that by 16. So the time is given in seconds. I replace the t by 3. 16 times 3 is 48. 48 times 3 is 144. So in 3 seconds, a freely falling body will fall 144 feet in a vacuum. Now I reverse the problem. Now the problem is, I know how far the object has to fall. I want to know how long it's going to take to do it. In other words, I'm going to drop something. I know I'm dropping it 400 feet. I want to know how much time to allow for that thing to hit the ground. And by the way, that is a scientific formula for how people test the depth of a well. What you do is you drop a stone, okay, free fall. You know how long it takes for the stone to, you know how fast the stone is falling. So you time how long it takes. Knowing how long it takes, you know how long it took to fall down. Then you have to remember that the sound has to come back to your ear, and you know the speed of sound. So the algebraic formula is what? You compute the free fall for the stone to hit the water, measure the time back for it to reach your ear, and you estimate the depth of the well from that particular point of view. Whole bunch of ways that you use the formula once you're not afraid of the formula. But basically, see, now the problem says, how long does it take for the object to fall 400 feet? See, in this case, you replace the d by the 400. And now do you see what happens? You want the t by itself. That's inside the parentheses. The 16 is multiplying the parentheses. To get rid of multiplying by 16, you divide by 16. If you divide by 16 on one side, you have to divide by 16 on the other side. 400 divided by 16 is 25. That says the square of t is 25. How do you undo taking the square of a number? You take the square root. And the square root of 25 is 5. And in fact, if we go back to this method over here, watch what happens. See, if the object falls 400 feet, to reverse the steps, instead of multiplying by 16, we divide by 16. 400 divided by 16 is 25. And now to undo squaring, we take the square root. The square root of 25 is 5. That's precisely the steps that we did over here. Do you see how this works? Did you have to understand where this formula came from to use it? No. But the more you understand about the formula, the more you'll also understand its limitations. Let me show you a couple of places where I've seen students in engineering use these formulas incorrectly. I say an object is 200 feet above the ground. How far will it fall in 5 seconds? Kid says, well, let's see. The formula is distance equals 16 t squared. I'll replace t by 5. In fact, I'm doing the inverse of the problem I just did. 5 times 5 is 25. 25 times 16 is 400. And they say that the answer is 400 feet. What's wrong with that? The object was only 200 feet above the ground. You see, the formula that says d equals 16t squared, that doesn't work forever. In fact, it doesn't even start to work till I drop the object. How fast is this pen falling right now? It's not. You can't say, hey, isn't it d equals 16t squared? No, that formula doesn't apply until I let go of the pen. It's not falling at all. And then that d equals 16t squared only applies until the object hits the ground. Then it stops. See, that's also a very important point that comes up in calculus, believe it or not. The idea of when something stopped of its own accord and when it was forced to stop by the intervention of a foreign matter. But we'll talk about that, hopefully, 4 or 5 courses from now. Okay? I hope you'll stay with me. I'm having a good time. Why shouldn't you? Okay? Now, the other thing I want you to understand in these formulas is you have to understand that you've got to be able not only to understand what these symbols mean, but what the labels are. In this formula, what noun did d modify? D was the distance in what? Feet. And what noun did t modify? T was the time in what? Seconds. Here's the trick here. It says, how far will the object fall in 1/30th of a minute? Well, people say, oh, I'll just replace t by 1/30th, right? That's the time. They square 1/30th. They multiply by 16. They put down the answer. That's the right answer to the wrong problem. That's how far the object would have fallen in 1/30th of a second. This problem says what? 1/30th of a minute. But the t that you put in here has to be in seconds. See, there are 60 seconds to a minute, so 1/30th of a minute is 1/30th of 60 seconds. That's 2 seconds. So you take the 2, multiply it by itself is 4. 4 times 16 is 64, so the answer is 64 feet here. But the person who uses this formula blindly doesn't even see this subtlety. Well, enough about that. Let me give you one more interesting formula. And this is one that supposedly actually happened. There are some very famous names in the annals of math history that go through the ages. Euler, Gauss, a whole bunch of names. One of the names that's associated with the next problem is one that's associated with a man named Gauss, who was a genius. And the story is, as most geniuses go, he was kind of impatient. He was bored by school. And he grew up in a German school, German system, very rigid, okay? And he was talking in class one day, and the teacher got very annoyed by this. And so she decided to give him a very hard problem to teach him a lesson for talking in class. She made him add up the first 100 counting numbers. She said, add up all the whole numbers from 1 to 100. And that would keep most kids busy for a long time. Keep most grown-ups busy for a long time. Do you know what Gauss discovered? He noticed something very interesting. He noticed that if you added the first and the last number, you got 101. Okay? Now look what's happening here. As you're counting, as you go to the right, each number is increasing by 1, isn't it? If you go to the left, it's decreasing by 1. Therefore, if you read in from the ends, each pair should add up to be the same as the previous pair. Let's just check that out. How much is 2 plus 99? 101. How much is 3 plus 98? 101. See, reading from the ends, each pair adds up to 101. And how many pairs are there altogether? 50. So the teacher said to Gauss, this is the way the legend goes, add up all the numbers from 1 to 100, and he said 5,050. Then she spent the rest of her life checking it. Okay, but basically, this is a very famous problem in mathematics, and it's called summing an arithmetic progression. And it doesn't just work for 100, it works for any numbers. What it says is if you want to add up the first n counting numbers, basically what you do is take the last number. For example, in this case, the last number was 100. Multiply it by the next higher number, then divide by 2. Is that the same thing that we got? But to indicate that this works for other than 100, you say the sum of the first n numbers is n times n plus 1 over 2. Now, can you visualize where that may scare a particular person because there's too much algebra in here? That's a language problem. See, if this scares you, let me show you the next one. The next one says to add the first n numbers, start with whatever n you picked. Like if n was 8. If n was 8. You add 1, gives you 9. Then you multiply by the number you picked. That was 8. That's 72. Then you divide by 2. That gives you 36. And that says if you added the first 8 numbers, isn't this exciting? The answer should be 36. Well, one way to add them is to just add them all up. The other way is to notice that 8 plus 1 is 9, 2 plus 7 is 9, 3 plus 6 is 9, 4 plus 5 is 9, so you have 4 pairs of 9, which is 36. Well, see, for a problem like that, who really cares which way you do it? But suppose now the problem had been find the sum of all the whole numbers from 1 through 800. Can you visualize the list this would be even with a calculator? You would have to punch in what? Each of the numbers from 1 through 800. A 1-800 number. Yeah, that's good, huh? I just made that up. You get what you pay for. A 1-800 number. It was. Was it okay? Chris is not saying anything. Okay, I better get back to the subject then. See, you could add up these 800 numbers. That's going to take a long time. But you see, if you use the formula, in fact, if you don't want to use the formula, what you're saying is what? With 800 numbers, you're going to have 400 pairs, and each pair adds up to 801. But the way this works is n is 800, so 1 more than n is 801. So multiply 800 by 801, and always save the actual multiplication for last. Then divide by 2. 2 goes into 800 400 times. So it's 400 times 801, and the answer is 320,400. Pretty neat, isn't it? Do you see how quick a formula can help you? But here's the point I'm making again. If you trust the formula, if you trust that formula, can you handle it even if you don't know where it came from? Sure you can. And I'll show you an experiment that I do with my arithmetic students over students who are taking advanced algebra. I will go up to a student taking advanced algebra, and I'll say, for what value of n to the nearest tenth will n to the third plus n be 12? See, I say pick a number, raise it to the third power, add it to itself, and the answer is 12. What number did you pick? You know, I went over something too fast before. I should indicate something to you. Suppose I say to you, pick a number. I'm just going to write small over here. I hope you can read it. So I say pick a number. Then I say something like add 3. Then I say multiply by itself. Multiply it by itself. Then I say add 4. Then I tell you that the answer is 78. And now I say, what number did I pick? I want to show you what makes algebra hard. You know, in trying to show you what makes it easy, I may skip over a few things that hide the true picture. See, how would you reverse the steps here? You say, well, look, I had the 78 after I added the 4. So before I added the 4, how would I find out what I had? Wouldn't I just subtract 4? See, 78 minus 4 is 77. Now the next command says, multiply by the number you picked. Multiply by the number you picked. So that means what? Divide by the number you picked. But if you knew what number you picked, you wouldn't be doing this problem. See, you get stuck at this step now because you don't know the number you picked. See, the same thing is happening over here. You see, this says pick a number, raise it to the third power, add itself to it. The answer is 12. Well, to undo adding the number to itself, you subtract it, but you don't know what that number is. So the algebra student has great difficulty doing this problem. But the arithmetic student who isn't afraid does this by the Goldilocks and the 3 bears method. He says, let's see, I'll take a wild guess. I'll try 1. If I replace n by 1, 1 to the third power, and what does 1 to the third mean? 1 times 1 times 1, which is still 1. 1 plus 1 is 2, so when n is 1, the output here is 2. That's too small. See, we're looking for 12. If n is 2, 2 to the third power, this is tricky. It's not 6, it's 8. See, 2 times 2 is 4, times 2 is 8. 8 plus 2 is 10. That's still too small. So I'll try 3. 3 to the third power. 3 times 3 is 9, times 3 is 27, plus 3 is 30. That's too big. You see, 12 is in here. So right away, I know that the answer is between 2 and 3, but close to 2. The problem is they want the answer to the nearest tenth. So now what I say is, okay, what's the first tenth that comes after 2? It's 2.1. So now I replace n by 2.1. I get 2.1 to the third power plus 2.1. I won't go through these details with you. The point is that with a calculator, it doesn't take long to do this. When you replace n by 2.1, you get 11.361, which is a little bit too small to be 12. Then you try 2.2. 2.2 to the third power plus 2.2 gives you 12.84. That's a little bit too big to be 12. So now you know that whatever the right answer is, it's between 2.1 and 2.2. And you see, the important thing is, I don't have to start with the answer and work back. I can start with the pick a number, see where it brings me to. If it's too small, I try something bigger. If it's too big, I try something smaller. In fact, watch what I do for the last step over here. See, I know I'm between 2.1 and 2.2. I don't know which one I'm closer to, so I split the difference. I take 2.15. When I take 2.15, when I replace n by 2.15, I get 2.15 to the third power plus 2.15. I did this on my calculator. I get 12.088375 for the answer. So I want to know what value of n gives me 12. I find out that 2.1 gave me 11.361. That's too small. 2.15 gave me 12.088375. That's too big. See, because I want 12. So where am I? I'm between the value that gave me this and the value that gave me that. That puts me between 2.1 and 2.15. If I'm in this part of the interval, I'm between 2.1 and 2.2. But since I'm not halfway yet to the nearest tenth, the answer is 2.1. Now, I hope that this gives you enough insight as to how you use formulas and the like. I also hope that this shows you how quickly algebra grows out of arithmetic. But I would like to summarize, where this is the end of our course, with a couple of personal remarks. Not nasty personal remarks, but personal remarks. I made a few at the beginning. I'd like to make a few at the end. One of the remarks I'd like to make is that if you have learned from this course, even if you don't know where you're going to use it, if you have learned from the course, what you have done is you have improved your ability to have confidence in yourself. You see, no matter what happens, the next time you're faced with a difficult decision, a difficult problem, and you're nervous, you'll be able to say, I remembered once when I felt I couldn't do something and I was able to succeed. Therefore, I think I can do it again. Success begets success. That's one thing I want you to be able to see from this. That's a very, very important thing. The second thing I would like you to see is that once you're not afraid of something, it's amazing how far you can come. You see, most people fail in math, not just because they can't do it, but because they're afraid of it. If you're not afraid of the subject, don't you think the odds are overwhelming that if you come to a problem that's tough, somebody in your research group, somebody in your support group knows how to do that problem? If you can even verbalize what it is that's bothering you, you'll find somebody who can help you. I have seen people in the social sciences skip an entire journal article because there was one equation in there and the equation frightened them. And you know what the paradox was? And the sad part was, you could have skipped that equation and not missed anything in the article. The person who wrote the article put the equation in for peer group acceptance. You see? But more importantly, I'd like to have you see the difference between book learning and education. Lots of people can teach you mechanical recipes. And lots of people can show you how tricks to solve certain problems. But there's something much, much more important that's going on here. It's a little game of life that says, let each of us attain all that we're capable of attaining. Let's grow to the maximum. Let's expand our horizons. Let me close this presentation with a true anecdote that happened with my oldest boy when he was very young. He had discovered the knobs in front of the television set, and he noticed that by fooling with the fine-tuning and things like this, he could change the picture. So he said to me, Dad, next time the television set goes bad, don't call a repairman, I'll fix it for you. And I felt very, very good that my son wanted to help me this way. And then he spoiled the whole thing. He says, and just give me the money you would have given him. Okay? So now I figured I had to teach him why people go out and charge money for this. So I went to the back of the set where all the color controls are, and I turned them all off. The red was off, the green was off. I put the blue on extra full. I guess that's what I did. And all of a sudden we have this very blue picture. And I said to him, Harold, fix the set for me. And he fiddled with those knobs in front, and he fiddled, and he couldn't do anything with that. And he finally confessed he didn't know how to fix a television set. Here's the parable I want to share with you. The human mind has two sets of knobs, just like a television set. There are the knobs in front that anybody can play with. Those are called the mechanical skills, the rote memory, whatever you want to call it. But there's another set of knobs in the back that control you as a human being, that make you the person that you are, that allows you to inquire, to expand your horizons and the like. When the knobs in back are working right, no matter how much people fool with the knobs in front, they can't hurt you too much. But if those knobs in back aren't working right, no matter how much you fool with the knobs in front, the picture don't get any better. And what I'd like you to feel in this particular course, if you found it painful, if you found it a growth experience, that what I was trying to do, without meaning it in a personal, pervasive way, I was trying to reach into the back of your mind and adjust those knobs that will allow you to grow to all that you're capable of attaining. And if I can ever be of any help to you in future courses, in future information, you should feel free to get in touch with me. With respect to addresses, it will always be kept updated by our office. I'll be happy to help any of you at any time. And may the years ahead for all of you be filled with good health, much happiness, great personal fulfillment. And whether I see you again or not, what am I going to tell you? Work hard, have fun, and stay young.